third lecture. He's the one who's going to be really heavy duty, so hopefully we'll.
No, it's not. I don't give a heavy
Good.
duty.
Anyway, it's a fascinating problem, and we're looking forward to learn about it. Thanks.
Hi, yeah. All right, so I want to tell you today about the value of errors in proofs. I'm sure you appreciate it. It's not what you think, but I'll explain exactly what I mean. It's really a story about the evolution of proof systems within computational complexity theory, which is my field. So I'll explain everything in this title. I really want to get to the end with this breakthrough result I mentioned, MIP star equal RE. That should be meaningless, but hopefully at the end of the talk will be perfectly understood and why it's so important for math. Okay, so the plan of the talk, I want to tell you about this value of errors in proofs and the impact it has on lots of things, science, technology, some philosophical points and mathematics, but I'll mainly focus on the conceptual part. Will not be very technical. I mean, there will be lots of conceptual notions, but not very technical. Before I tell you about the value of errors in proofs, I have to tell you about value of errors in algorithms. And even before that, I want to talk a bit about the connection between proofs and computations. But really, the main purpose is just a demonstration of one of the nice stories we can tell in complexity theory of an evolution of an idea. There are many other stories I could have talked about. Today it's about proof systems and the notion of proof. Feel free to ask questions if something is not understood. So proofs and computation have gone along together for millennia. I want to mention 2 points in this long history. One is the famous Euclid elements. We all read it as basically a collection of theorems in plane geometry proved in the first deductive system from 5 simple axioms. But really, if you read any proofs there, or all of them, they actually are effective. They actually give you algorithms to construct the necessary points demonstrating the theorem using very simple operations, using a compass and using a straight edge. So in plane geometry, computations and proofs have the same power. We'll talk about the meaning of that. Whatever you can prove, you can actually generate an algorithm for. Go 2,000 years ahead, we go to the turn of the 20th. Skip a lot, yeah, skip a lot. That's another lecture. Hilbert, as everybody I'm sure knows, has this amazing dream that in mathematics, truth is the same as probability. Everything correct, everything true you can prove, and everything you can prove you can find by what he calls the mechanical procedure. This dream, we know, was shattered completely, first by Gödel in his incompleteness theorem, showing the first equation is wrong, and then by Turing showing the second one is wrong. That's his undecidability theorem. What did Turing do? He really, in order to prove undecidability, he had to give meaning to what Hilbert meant when he talks about mechanical procedure. So he defined there are more rooms on the other side, I guess. So Turing defined formally, mathematically, what an algorithm is. That's his famous Turing machine. As a byproduct, we all know this created the computer revolution, but we are not going to talk about this minor thing. We are doing math here, so I'm going to talk about algorithms in this talk only for decision problems, right? So what's a decision problem is some set S, subset of some universe. We get an element in this universe, and we want to know whether it's in the set or not. Okay, that's a decision problem. And implicitly defined 2 classes, the sets that can be computed by finite algorithms, algorithms which always hold, and correctly give the output for every element. And RE are the sets provable to finite algorithms. So this means that for every element, some powerful prover can convince anybody else that this element is in the set. And famously, his undecidability theorem can be stated. What's the difference between
R and RE?
Yes, so R, there's an algorithm that can decide by itself whether X is in the set. That's decidable, yeah. And the RE is something that someone can do for you and just convince you that somebody gives the proof and you verify it. So undecidability, it's important to get the difference. So it's, let me spend some time on it. I'll tell you, I'll tell you in the, yeah.
Not a good use of the word two.
Well, I'm proving a theorem to you. That's if I'm proving a theorem to you, that's okay, right? Yeah. So you are a finite algorithm, and I can give you a proof you didn't know.
Is it?
So let me just. I'm sure many of you know what the problem separating these two classes are, right? The undecidability of the problem of whether a Turing machine holds or not. Or if you want, just a second, or you want to clarify something.
I just want to make sure I understand the answer to Dennis's question. Is that one of them is an algorithm that outputs a list of everything in the set, and the other one, just given an element, tells you yes or no, it's in the set?
That's one way to think about it. I prefer that in both cases, you get an element, and you have to decide whether it's in the set or not. In the first case, R, the decidable problems, you should do it on your own. You have an algorithm to decide yes or no, and you stop. In the second, you can get help from God or anybody who knows, you can get this help from an unbounded entity that just convinces you that this is in the set. And the best example is, Turing's example, whether a Turing machine holds. He proves that this is undecidable, so no algorithm can tell a halting Turing machine from non-halting machine. But if I told you that it will run for, a zillion steps and halt, you can verify this, right? You run for a zillion steps and see whether, Okay, so he proves this.
One is, I still don't know the difference.
Okay, so maybe.
Which one's smaller?
Which one's smaller? R is smaller. R is smaller. Everything you can do with without a prover, you can do with a prover that does nothing. Okay? Everything you can do without help, you can do with help.
What's the definition of RE?
RE are all the sets, the collection of all sets, such as for each of them, there is a way for a prover to convince you that there is a prover, an entity that can convince you that X is in the set. Okay, this is math, but I'll take then, the other suggestion. Here's a different definition. There's an algorithm which lists all the elements in S. That's RE.
Which doesn't need to be finite.
Right. It cannot be finite if S is infinite, but it lists every element in S will be printed at some finite time, which you don't know. So that's RE. So it's bigger, clearly, and they are different. Okay. One point to make is if you change finite to efficient algorithms as opposed to just algorithms which hold, when efficient I mean, let's say, polynomial time in the length of the input, then this is really the same question which we are fighting with, the P versus NP question. It's just the same question about the difference between computing something and proving something. And that's open. Okay, so I want to just start with a bunch of examples of, the notions that will pop up in this lecture: claims, arguments, proofs, proof systems. So what is a convincing argument? We want convincing arguments for this type of claims. X is in some set, and we imagine two entities there, a verifier, someone who wants to know the answer, but maybe is limited, cannot have, doesn't know how to figure it out, and a prover, someone is infinitely clever, but someone you cannot trust. I mean, if he tells you X is in S, it says, I can prove the Riemann hypothesis, you maybe doubt it. Okay, and then, the prover, like in math, I mean, writes a paper and sends it to anybody, and then anybody can verify this argument. So let's see some examples. This basically high-level view of proof systems. Here's the proof system for composite numbers. A typical claim is this number is composite. Here's an argument for it, two smaller numbers that the claim is multiplied to this one. And the verification, a verifier, would just check, will do the multiplication and figure out whether it gives back the input, right? So this clearly, sound and complete. Only your composite numbers will have proofs. Prime numbers will not have such proofs. It's a very efficient algorithm, right? It's just multiplication. And in general, of course, works for any number. So that's a proof system for the composite numbers. The set of theorems in the proof system is the set of composite numbers. So I'm just, getting you used to the language. That's a set of theorems in this simple proof system. The argument, we don't care how complicated it is to generate, right? Cryptography, of course, assumes that it's difficult. So we don't care how complicated. Verification has to be efficient. Okay, here's another example where familiar, the claim is that this puzzle is solvable. An argument will be just filling it up with the missing numbers. Verification, of course, is very simple. You just check the Sudoku rules. So that's very efficient. It's just pattern matching, really. And it's really general. I mean, of course, you realize that Sudoku doesn't have to be 3 by 3. It can be bigger. The theorems here are all the solvable Sudoku puzzles. So this, you can, there are infinitely many inputs in this problem also. Here's a familiar one, like the plane geometry, this piano arithmetic, or lots of other deductive proof systems in math. Basically, the objects you manipulate are formulas over integers. You have a bunch of axioms that you are familiar with. And then you have deduction rules, how to infer one formula from several others, like modus ponens here. What's an argument for a claim, some formula? So you claim some formula is a tautology. C, it's just a sequence of other formulas where each one is either an axiom or follows from previous ones by the deduction rule. So by deduction rules. So again, also in this proof system, it's very easy to verify. Given a proof, whether it's correct or not, you just check whether, each one in the list is either an axiom or follows from the others. So again, verification is efficient. And the set of theorems here is maybe more interesting than the previous two. I mean, you get all these, number theoretic statements that you can prove in this system. So what, we can now get the essence of proof systems in general. This is something we like to do in complexity theory, just have a classes of objects, the class of proof systems. What we want, essential were completeness, namely true claims have proofs, soundness, false claims don't have proofs, and efficiency. It is easy to verify whether, it's easy to distinguish the two cases, whether a given argument is convincing or not. And again, efficient will use polynomial time, although many other notions were studied. We'll fix this for now. So more formally, so that this complexity theoretic view translates here to formal definition of what proof systems are. Of course, math is full of proof systems, but they all fall in this category. Again, repeating what I said more formally, proof system is simply defined by its verification algorithm. Okay, it's an algorithm that takes two inputs, one calls a claim, the other an argument, and it satisfies this condition. So if the claim is true, namely x is in S, then some argument convinces the verifier to accept. And if, this is the happy case, right, where we call the claim we call a theorem, the argument is called the proof. And on the other hand, if the claim is false, then no matter what argument is supplied as input, the verifier will reject. Okay, so for every such verifier, such algorithm, there's a set of theorems that this proof system proves, like in all the examples we saw. And in fact, NP can be simply defined as the collection of these sets, where this verifier is just a deterministic, efficient algorithm. So we have these examples of sets of theorems. And P, the class P, polynomial time computable problems, it really is a set of, the collection of sets of theorems where a verifier exists that doesn't look at the argument, can do it by itself. So again, this is a way to express P versus NP in this language. Okay, so good. This is all classical stuff. This is normal proof systems in math. I want to move now to proof systems that have errors. So before them, I want to talk about algorithms that make errors, randomized algorithms. Here's a crash course. It's one page. I'm sure all of you have seen probabilistic algorithms. So, we start from, this observation that nature seems to produce, unpredictable events, or maybe access to randomness. That's what I was talking about yesterday. So why not let algorithms use random choices? That's the point. So the algorithms that are probabilistic differ from deterministic one in a very simple way. In deterministic algorithm, but if it computes some function f, then this algorithm always produces f of x. It doesn't have choices. It just works and produces the correct answer always. A probabilistic algorithm is allowed to make random choices, and so the output is a random variable. What you demand from this random variable is it will equal the function value with high probability. That's the difference. So it's still of value, right? Because this algorithm still uniquely determines the function. This number is bigger than 1/2, let's say 2/3. So that's where we introduce error in algorithms. We still allow some error in the computation here. And this 2/3 is pretty arbitrary. If you have an algorithm like this, you can easily reduce the error as much as you want. For example, if you have the error was 1/3 as before, you run the algorithm independently k times, it will reduce the error to be exponentially small in k. So pick any number bigger than 1/2. So what's the value of allowing errors in algorithms? We don't like errors, of course, but it seems we can solve more problems efficiently with randomization. We don't know that it's, we just seem to. That was really what I talked about yesterday. Oops. Wow. Very interesting. I wonder if I said something offensive to the institution here. What's the reason we tolerate errors? I claim that we tolerate errors everywhere. We cross the street and we are not sure absolutely we'll get to the other side. So why not allow it in algorithms? So anyway, sorry? Yeah, absolutely. That's a very good point. Yeah, it happens all the time. Okay, this is actually a much better situation, right? In this or crossing the street, you cannot reduce the error arbitrarily. Here you can. So anyway, so these are parts of life, probabilistic algorithms. We see them around us all the time and use them. Okay, now we want to import this to proof systems. And I claim this is easy because we define proof systems by algorithms, right? A proof system was an algorithm. Good, so let's do it. Maybe. Anyway, so we want to put it into proof systems. These are coming from papers in '85, two independent papers, one motivated by cryptography, one motivated by group theory. We have our classical definition of a proof system, and we change it in the obvious way. We allow the verifier to be probabilistic, okay? And we allow errors. So we want these statements, completeness and soundness, to just hold with high probability, okay? So at least it's a clear definition, clear mathematical definition of what a probabilistic proof system is, right? Yeah, of course.
In this case,
Is it just high probability for the right result or some distribution?
Right, you want completeness and soundness with high probability. So the probability over the random choices of this algorithm, V, the probability that you decide incorrectly, whether it's true or false a claim, is small, right? So with very high probability, you know whether the claim is true or it is false, okay?
Just the average, not the distribution.
No, not distribution, just the output. That it's a yes/no thing. You believe it, believe the claim or not. The claim is again some input is in some set, okay? But you get, of course, the argument, right? So so you just allow error, and you know it's just like what happened in the previous slide. We allow error in proofs. But of course, it's very different, at least psychologically, I claim, for mathematicians. Proofs are what's supposed to, it's holy. What's supposed to be the distinguishing feature of math from all other disciplines. We know absolute truth when we have a proof. So we allow errors, and it seems like, a weird thing to do, but we'll flow with it. We'll see that, there's value in considering this idea. At any rate, it's a proof system, well defined. We can still have all the theorems in this system. And as before, defining NP, now we define IP, the class of all sets which are theorems in this kind of proof systems. But I didn't tell you the complete definition of these proof systems. I already told you it's randomized, but I'm going to add another feature to this proof system. This is interactive. I'll show it in the next slide, but that's the reason it's called IP, for interaction. So what's the full definition of an interactive probabilistic proof system that came out in these papers? I'll contrast it with the usual NP definition, where in NP we had the deterministic verifier, which was always correct. In IP, as I said, we have probabilistic verifier that sometimes makes error, but with a low probability. And the other difference is this argument. In the NP proof system or in mathematics, you write a paper and you send it off. Here, we allow interaction between the prover and the verifier. So, like maybe happens when you discuss a math problem or a theorem with your colleague, you may ask clarifications. You go through an interaction at the end of which you either convinced that the proof is correct or not. So, so that's the definition. That's the full definition. Interactive proof systems allow interaction, allow randomization by the verifier, and allow small amount of error with low probability. So clearly it can simulate the classical ones. The question is how much more powerful are they? Yeah, sorry.
Does the notion of interactivity also make sense in the deterministic setting?
Yeah, it does. You can have an interactive deterministic system, but you should realize quickly that it's useless because you can simulate it. If the verifier is deterministic, you know what the question he will ask. You answer all questions in advance. So no need for interaction. That's a very good point. And in the randomized case, it's impossible to know what the verifier will ask because it can potentially would have asked exponentially many questions. So that's an important difference, right? That's a very good point. Okay, so there's a new model here. And like all new model, new computational model, new model of proofs, should ask yourself whether it's a reasonable model. This is something you should ask in every model you suggest. It doesn't mean you shouldn't study unreasonable models. You should. But in this case, I claim it's quite reasonable. I mean, first of all, the error part, this was motivated not from Riemann hypothesis proofs point of view, but really from computation, maybe cryptographic motivation, where the type of theorems you prove to other people is I picked my public key according to the protocol or something. Not something that you know, math is hanging on, but practical matter. So the other reason is, of course, interaction is very natural. So adding interaction is is natural. Anyway, we are going to study this model. Reasonable or not, I want to stress that this is absolutely a revolutionary scientific notion. The impact of this idea of this definition has been amazing. I'm not going to talk much about it. It has both, scientific and technological impacts. I'm going to talk mainly about the math side and the conceptual side. There are many variations, of course. I'm not going to talk about them that are also practically important. We will not discuss them. I want to mainly talk about how this allows proofs to have properties that are completely paradoxical and we do not expect or provably cannot be attained by normal classical deterministic proof systems. The two I'll mention is the zero-knowledge proof systems and probabilistically checkable proofs. I'll explain them, so I won't do it now. But one point is that this, ideas of introducing more and more proof systems with these properties led us to even more proof systems, in particular proof systems that were mentioned in the title with multiple provers. We'll get to them, and eventually to quantum proof systems that I talk about at the end. Okay, so it's a story of a journey. The first one, proof system with paradoxical properties is this zero-knowledge interactive proof system. And it was in the original paper, suggested in the original paper which defined IP. So zero-knowledge IP, what kind of proof system is this? It's the normal IP proof system. I should note that, the formal definition is quite technical, but the intuition is very simple, and it really captures, the formal definition captures this, but it's enough to know the intuition. It's a normal interactive proof, so it should have completeness and soundness with high probability, as we discussed. Plus, there is a demand that whenever the verifier accepts, namely the claim is true, it learns absolutely nothing about the proof. So it is convinced that the claim is true, and nevertheless it learns absolutely nothing it didn't know before, certainly not about the proof and not about anything else. So Dennis told me before the talk that he doesn't care about proofs, he cares about understanding. These are proofs which you get zero understanding from, zero. But you are still convinced that, it's true. So this looks ridiculous if you never saw it before, especially if you try to convince anybody about anything they didn't believe without providing any information. So let's see. So it's a question, they ask this question, which type of claims can have such proofs? And can convincing proof be uninformative? And you can think about trying to convince somebody of some proof in math without telling them anything they didn't know. Nevertheless, this question has an answer which is surprising, namely that not just, sorry.
Could you go into a little bit more detail about how you're formalizing what it means for proof to be uninformative?
If you want. Yeah. No. I'll say a couple of sentences. Of course, the answer is longer, but yeah. So the way you formalize it is the following. You want that in every case the verifier accepts so it accepts a conversation. Conversation is a random variable, right? Because it's randomized. So there is a distribution on convincing conversations for each particular true claim. Okay. You want that there will exist an algorithm that knows knows the verifier algorithm, of course. You want there to exist an algorithm that can generate a distribution which looks identical to that convincing distribution. Okay, so if you can generate a convincing conversation by yourself, you didn't learn anything. All right? Good. We'll see as students provide a little more than that. But that's the formal definition. Yeah, so it turns out that everything that is provable in zero knowledge. That's a theorem. We proved it a year after this paper, and this theorem has an assumption. It has an assumption that cryptography can be used, namely that one-way functions exist. For example, factoring is a hard problem. So it uses cryptography, and cryptography is used to say that the two distributions I talked about, the real conversation and the simulated conversation, may not be identical, but you cannot tell them apart. Okay? So you don't learn anything in this sense. You could not have gained any information in your lifetime about this proof. Okay, so this is a theorem under this assumption that we all believe if we shop online, right? So under cryptography. So such proofs are possible, and this led us to another question that led us to another proof system. I should mention that these zero-knowledge proofs are a very important concept, and it has theoretical applications. It's absolutely critical in designing, in general, cryptographic protocols. Lots of systems. In fact, when 30 years ago, 40 years ago, it is amazing. I was giving talks about it. I said, it's a theoretical idea that's sort of surprising, but it will never be implemented. And I was wrong. I mean, enough motivation got people to actually simplify the protocols, and there are plenty of applications which today use zero knowledge. There are extensions of this idea to the physical realm, in particular one really ingenious one to nuclear disarmament that I understand got into some steps in the of nuclear missiles between the US and Russia. Maybe could have been potentially implemented. And also to things like DNA testing, things where you want, you have several samples of DNA of people, you want to be able to locate the one that maybe is associated with the crime, with the other knowledge disappearing. You don't want to have innocent people's DNA in your stuff like that. There are many ingenious zero-knowledge physical systems. But I want to tell you about how it led to new proof systems, in particular the one with multiple provers. So here's again the slide about this zero knowledge, and I mentioned that it had this assumption in it, namely that one with some complexity theoretic assumption like factoring is hard. And we were wondering whether this assumption is needed. We can prove the theorem with it. Can we prove it without this theorem? And is cryptography necessary for zero knowledge? And the answer, like many many questions, is yes and no. So we can prove with Ostrovsky, we prove that it's essential. So it cannot be removed. If you have a zero knowledge proof for anything non-trivial, then you get immediately cryptography. But on the other hand, the answer can be yes. It can be whatever. No, yes. It can be removed if, like we do again in many times in math, we change the model or change the question. So here's we came up with a new model of proof systems. So this, again, we have a new type of proof systems. These are proof systems in which there's not one prover, but two. Or in fact, you allow 3 or 4, or many. But let's exemplify it with 2. So how does this work, this proof system? It's just like before. We insist on the usual things of completeness and soundness, and the interaction is limited in the following way. There is a claim well known to all these parties that the claim is that some element is in some set. The provers, the two provers or many provers can talk to each other, devise a strategy, how they want to convince the verifier of this claim, and then they are separated, and the verifier can interrogate each of them separately. They cannot talk to each other afterwards. I mean, when he starts asking questions. And there are questions asked, coins tossed, and eventually the verifier decides to accept or reject, I guess, this challenge. I wonder why this happened.
I think it's every 20 minutes about. So.
Okay. So, time out. All right. Weird way to do it, but anyway. Right, so that's a model. And what we were able to prove about it is that here zero knowledge can be obtained without any assumptions. So in some sense, what's really happening is this physical separation of the provers replaces this computational assumption of cryptography. I'm not going into explaining it more, but that's roughly what happens. Anyway, it's a new model, and you can ask, like before, whether it's a reasonable model. I can tell you 2 stories about it, why it may be reasonable. One, this is the way police interrogates, let's say, 2 suspects of a crime by putting them in different cells and interrogate them separately for, consistency, say. So that, models, in some senses, situation in real life. Another story is that when we came up with this idea, this paper, the 2 institutions we were at, which are Hebrew University in Jerusalem and the MIT, wanted to patent it. I don't know whether it's a sign of reasonableness. They wanted to issue a patent where, maybe you'll go to your ATM with 2 cards that are separated by lead, and you will convince ATM that you are you, and you'll get the money, and it will be perfectly secure, no assumptions, no factoring, anything. We advised against it. They patented it anyway, and made nothing out of it. Although today it would have been different. Anyway, this is a model. We should study what. Yeah, sorry.
I'm a little confused how this can be done when you couldn't do it with one, because couldn't you consider the 2 provers to be one prover who's just restricted in the answers they give?
Well, restricted how?
In that there's some subset of the questions they ask, they say this is.
So if it's equivalent, why not look at this picture? I mean, you could define a prover who has 2 parts and is not, the 2 parts are not.
But ZK2IP is not contained in ZK-IP, for instance.
We don't know that. We don't know that. We don't know. We are struggling, as you see, to understand the computational power of these proof systems. Like we don't know whether NP equals P. We ask the same questions about these proof systems. They are growing and growing in power, but we understand some. I'm getting to that. Yeah. Okay. Yeah. This is the picture. So we defined a growing set of proof systems. NP, IP, 2IP, many IP, like many provers. And for a while, we just had trivial inclusions. Some of you may not know this acronym, but we understood that IP, for example, it can be simulated. So the computational power of statements it can prove is contained in polynomial space. Everything you can compute with polynomial time memory, maybe not in polynomial time, but space, polynomial memory. And 2IP, for example, we knew that anything provable there is computable in non-deterministic exponential time. That's the exponential version of NP. So we had these upper bounds on the power of these proof systems. People believed they were, this was very generous, but in fact, within a few years, we understood the power of these proof systems very precisely. So it turns out that these upper bounds were sharp, namely, interactive proofs is exactly, you can have a single proven interactive proof for every problem in polynomial space. You can have a two-proven interactive proof for every problem in non-deterministic exponential time. And I'll get to the third statement soon, but I want to say that in all these statements, they are, full of technical words about resources like space and time, but they all have conceptual meanings that are pretty, I think, surprising. For example, the first statement really says that winning strategies in games can be efficiently verifiable. What I mean by that is, suppose tomorrow some alien landed here and claimed to have a winning strategy in chess. We could check this efficiently, right? Checking, not that he wins against us in every game, check that indeed the claim that this entity has a winning strategy in chess could be verified by us, by efficient verifiers with very high probability. This is strange because this statement is not about the existence of a solution to a system of equations. It's a statement with many quantifiers for, there's a move, so whatever other move is done, there's a move, right? So it doesn't look like it should be, efficiently verified in normal proof systems. In IP, it can. The statement about many prover IP containing non-deterministic exponential time is quite surprising because non-deterministic exponential time is different than P. So it contains problems that cannot be efficiently solvable, that require exponential time. Nevertheless, problems that require exponential time, and in fact have exponential long arguments, can be verified efficiently. So it's another very surprising result. And the third one is about a new proof system that I didn't define yet, the PCP, probabilistically checkable proof, that I'll describe now, that turns out to characterize a class, a classical class NP. All these theorems, they have no assumptions in them, pure mathematical theorems. So I want to talk about this second surprising or paradoxical proof system, which is PCP. I don't know, how many people heard about it? All right. So it's back to the normal non-interactive proof system. There's no interaction, there is randomness. So here's the PCP proof system. It looks just like the NP proof system, right? So only the verifier is probabilistic, and we allow some tiny error, but the prover sends one message to the verifier. But again, we put a restriction, and the restriction here is very severe. We allow the verifier to read only 20 bits in the argument. Can be random locations, but only 20, or some constant that you can choose. Okay, no matter how long the argument is. This seems totally ridiculous, maybe as ridiculous as the zero-knowledge one. I mean, how can you find a bug in a 100-page proof when you are reading 20 bits of the argument? Nevertheless, can you do it? Maybe, I don't know what Andrew Wiles is working on now, but maybe it's a Riemann hypothesis. And eventually, when it provides, the 100-page or 1,000-page proof, we are supposed to verify this by reading 20 bits. So how can we do it, or when can we do it? And again, the answer is universal. You can always do it. Every proof, every mathematical proof can be converted efficiently to another proof, another written proof, that can be verified this way. In other words, you take any proof, and there is this efficient procedure, not knowing whether it's a bug or not, but having the property that if the proof was correct, the new proof will be correct. If the first proof had a bug somewhere, the new proof will have bugs everywhere, so that random sampling will catch it. So again, very surprising. This is our result, that PCP equals NP, everything provable. NP is provable by the snapshot proofs. Yeah, this is supposed to be the killer application of this theorem, but of course we don't have it yet. But it has a huge impact, and the impact is mainly in the area of optimization. Because of this theorem, we can now prove NP hardness, hardness of obtaining approximate solutions to optimization problems. NP completeness typically tell you finding the optimum is hard. This can tell you finding a factor of 2 approximation or factor log n approximation is hard as well. Has many implications in coding theory, in complexity theory that I'm not going into. Now, it's a fundamental theorem, fundamental understanding of the class NP.
So I suppose the proof could become much longer when you...
Yes, but since it's an efficient procedure, it's not much longer. So in the beginning it was polynomial time, maybe it was n to the 100. Today we know that it can be done in something like n log n or n log squared n. So nearly linear time and length. Yeah. And that's, again, very important for hardness of approximation reduction, to have this very efficient reductions. Yeah. Yeah, and this too is implemented, now in particular in blockchain systems, and very important to cloud computing also, to delegation of computation. Okay, so now I'm very good at getting to my last part of the talk. So I told you about these 2 or 3 major results regarding probabilistic interactive proofs, and we are going to again extend the model, and instead of randomized machines, we allow the verifiers and the provers to be quantum. So again, I need to give you a 1-page, introduction to quantum computing, like I did with probabilistic computing. Again, I assume many of you have seen it, but anyway, I'll go through some basics. Again, the way it happened, that quantum computing came to the fore, quantum mechanics seems to govern our world. And why not use quantum phenomena in algorithms? Like, why not use randomness in algorithms? This was suggested by independently by Feynman and by Manning. Suggested that we integrate it into algorithms. And the new ability it suggests by quantum mechanics is you can manipulate superpositions of bits. So you can simultaneously act on all 2 to the n possibilities of a 2n string using unitary operations. It took some time to formalize this model, to make it the analog of Turing machine, a quantum Turing machine. And the classes, this BQP is supposed to capture the class of all problems solvable by efficient quantum algorithms. We know that it is at least as strong as probabilistic machines, but we don't know the power of these quantum algorithms. And then people try to see what kind of problems can be solved efficiently in this model. And after a few small examples, there was this, earth-shattering event where Peter Shor proved that in this model you can efficiently solve both factoring integers and compute discrete logarithms. I'm saying this was a major event simply because these are the very problems that whose difficulty underlies security systems on the internet. So clearly this had an impact, and the impact was frenzied attempts to develop many things. First of all, build quantum computers, build generate the technology and build general purpose quantum computers. So far, it's been many years, 90 years, 30 years. billions and billions were invested and are still being invested by governments, by companies, and yeah, we still don't have it. We have a lot of technology developed, but we don't have general purpose quantum computers. If you want to factor integers, maybe the largest number you can factor today is 65, or maybe somewhat higher. So it's not doing that, but it's doing other things. In fact, the original suggestion by Feynman was that we should have quantum computers in order to simulate quantum phenomena. And this we can do to some extent. People immediately, of course, try to develop, since these hardness assumptions may not be hard anymore when quantum computers exist. We may want to protect our secrets with something else. So people are developing what's called post-quantum cryptography, finding other assumptions and replacing systems under these assumptions, like some lattice problems, for example. People are still trying to find new quantum algorithms, just explore the power of this model. But what I want to focus on, as the rest of the whole talk, is about new proof systems. So what are quantum proof systems? Again, we have our template. We simply let the verifier be a quantum algorithm, and the provers too, because they may communicate with quantum bits. First, there was this suggestion. This is the analog. When I put star, I mean quantum. So it's the same one prover proof system with in the quantum world. And it took some decades, it was much longer than it took the classical case, to prove that quantum doesn't add any power to one single prover proof system. Okay? So it's the same as the classical one IP, which is p-space. So that took some time. It took a lot of technical development, mathematical techniques, and using many of the machinery that was developed for PCPs and so on. So this was solved. We understood quantum single prover proof system. And then in parallel, people suggested multiple prover proof systems with quantum agents. And also this took time, even showing that quantum proof systems are at least as strong as classical proof systems with multiple provers. It's not obvious because you increase both the power of the prover and of the verifier. They are both becoming quantum, and it's not obvious, at least, that this inclusion. This took time.
Do you have to do that? Could you only make the verifier?
You can make the verifier on, yeah.
Okay.
Yeah.
But for some
yeah, no, it will not make a lot of sense if, well, I don't know. Yeah, you could do that, and I guess it was done, but it's natural to make them all quantum. And then, people believed that, soon you will get, like in the single prover case, you will get equality. But in fact, several years later, these guys proved that you can do much more than in classical, classical multi-prover systems. Even doubly exponential time problems can be proved to an efficient verifier in this model. And then it was not clear where it's going to stop. And it stopped in an amazing place. It stopped where this paper showed that anything in the class RE, so I remind you, anything that, this class of undecidable problems that are reducible to the halting problem of Turing machine or to the solution to the Fountain equations, can be proved to an efficient verifier. And this, at this point, looked really bizarre, and this was maybe a point telling these complexity theories that they've gone berserk, and they generalize their proof systems to to get proofs to do something that's completely unreasonable, prove undecidable things, and maybe the sandbox we built for ourselves is ridiculous. So it was maybe even more shocking, although this was already understood by the time this proof came about, that it's much more real and much more important than to mathematics, to classical mathematics and physics, than you would think. This result gave counterexamples to major conjectures in math and physics. It resolved this Wigderson problem. This has to do with notions of measurements that I'm not going to get into. But anyway, it resolved a major question in quantum information theory. It gave a counterexample to the Korn's embedding conjecture. This is a conjecture for Neumann algebras and in group theory, and by now we know more. So somehow this model is not as ridiculous as you might think. It connects to real, important problems in this field. So I want to talk in the last 5 minutes. I'm blaming Dennis for asking me many questions at the beginning, so I'll take a few minutes more, just to tell you a little bit about, how this all fits with some things you may know or may have heard about. And it already started in the paper defining this class of proof systems, connecting them to, I'll mention it again, to well-known things in physics, so let me go there. So one thing to know, this was already understood in the classical case, that when you have two prover systems, then it's enough to have one round of communication. The verifier asks one question of each prover, gets one answer, and then decides what to do. So you don't need a claim, in fact. You just want to understand what is the maximum convincing probability under the best strategy of the provers that they can convince the verifier. So the true claims has this number bigger than 2/3, maybe. Otherwise, it's less than 1/3. So we want to understand this value. You can think of it as a game, G, defined by the verifier computation. The verifier is a function of these 4 variables. The questions and the answers should determine whether it accepts or rejects. So there's some value between 0 and 1, the probability that it accepts. Okay, so that's a classical story. That's how to think about two-prover classical games. And it turns out that it doesn't matter if you allow the two provers. They are not allowed to talk, but they may have access to a common random string, so maybe some limited form of communication. In the quantum case, it's the same thing, only that the two provers are now allowed to share a quantum state, an entangled state. So they can be entangled. They are not communicating directly, but they can measure entangled states. And you can define the same value. I mean, if there is a function of the verifier, what's the highest probability that quantum provers can convince this quantum verifier to accept? And these two numbers was the basic question of what's the relationship. For computer scientists, as I said before, the question is how complicated computationally is it to compute or to approximate these values, and we already know the answer to these questions. I mentioned it before. For physicists, this came up, the very same question came up a century ago. So at the Institute, 1935, the famous paper of Einstein, Podolsky, and Rosen, EPR, was questioning the validity of quantum mechanics, wanted to understand whether Einstein famously didn't believe it or didn't believe it is complete. So they had the same picture. It didn't look like that, but it looked like that. Right? So some of you may recognize this EPR experiment, this thought experiment with an event generating 2 photons which are entangled going in opposite directions at the speed of light. They are measured, and somehow information about the value seemed to propagate faster than the speed of light. That was the meaning of quantum mechanics being true or consequence. So they called this differently, not to IP. They called this quantum no-local game, and this possibility of showing an entangled state spooky action at the distance. That was Einstein's term. They also called the classical one. They wanted to explain this phenomena classically by local game using various hidden variables. And what they were able to do, these are the yeah, I'll mention in the next slide. What they were able to do is to show that indeed the value that, the probability that quantum provers can convince quantum verifiers, it can be higher in some games than the classical value. So saying it again, let me separate the physics and the computer science approaches. Physics was motivated by understanding whether quantum mechanics is complete, and they developed a variety of games which exhibit this phenomenon, really validate quantum mechanics. A variety of games where the quantum value is bigger than the classical value, which this started with the famous Bell inequalities, and it culminated really with tests, right? So we know today this EPR experiment was carried out 70s and 80s, and it's really true. In the CS world, this suggestion of the model MIP star already started, connecting it to EPR, and also suggesting not to look at the example, but to build a complexity theory in the same sense we do it for problems, for P, for NP. Look at all non-local games, look for completeness and amplification of game values and reductions between different games, and using all this technology of PCPs and codes. And it all goes into this proof, which is very complicated, maybe a 200-page paper, and relies on a lot of past work on classical interactive proofs, and implies the consequences in math and physics I mentioned. I should also mention that just a few months ago, this technology, so it seems to be a new technique in mathematics. So this MIP star, people developed the basic notions of it. Again, one can explain new proof systems if you want, very bizarre ones, or just build models for which you can have convinced some verifier of statements in like undecidability claims, and they are tailor-made to disprove other conjectures in mathematics, and this was recently proved. It's a conjecture in probability theory. The Aldous-Lyons conjecture is now known to be false by this type of techniques. Okay, so summing up, I showed you lots and lots of different proof systems, and we saw that allowing randomness and errors and interaction lead to proof systems with very weird properties. I mentioned that it has practical consequences, and this theory, this imagining models and understanding them led to quite a bit of things we use every day. It's these are general statements about complexity theory and the way it connects with, or both with the fields within itself and with math and physics in various ways. Somehow, to me, it shows that this methodology that we have of developing, thinking about classifying problems and understanding connections between them, even if we don't understand each, is very powerful. And like yesterday, if you want to read about this development, although not the last step because it's 5 years old, but lots of other topics in computational complexity theory, this book is free on my website, and it's supposed to be friendly. Thank you.
That's our wonderful talk. Any questions or comments? Chris?
So I want to make sure I understand the main thing, the MIP star equals RE.
Yeah.
So concretely, what does that mean? Like if I, like in the halting problem, if I give you a code and you have a quantum computer, you can, with high probability, decide if it halts or not? Or
Yes, with two provers. Yeah. So there are two provers. It turns out that the verifier can be classical. It turns out the provers have to be quantum and have to be entangled. And these two provers can look at the code of the Turing machine and can convince the verifier in polynomial time in the length of the code that it holds, or that it doesn't hold. Yeah.
There was another question there. Yes, there.
So originally, for the multiple prover, you were gaining, it seemed like you're gaining more power by separating them,
Yeah.
like prisoner's dilemma style. But then it almost seems like in the MIP star, you allow them an entangled state, so you're almost like having a weak.
Well, it's weak interaction, right? It's weak communication. They cannot send each other anything. They can measure the state. And actually, it's a good point. And to your question, one should wonder, seeing this result, how is this possible? After all, the whole problem with undecidability, with this halting problem, is, the reason it's undecidable is if the machine stops, we don't know when, right? So there's a parameter, time, which can be unbounded. And in this system, it's not clear what is unbounded, because time is bounded. This interaction happens in polynomial time, and the verifier decides in polynomial time. So what grows? And that's a good question. The answer is, what grows is the dimension of the Hilbert space in which the entanglement lives. So this can be unbounded, and that's, replaces time. So, yeah. More questions?
Can you explain the idea of the PCP?
Yeah, okay, so I cannot explain quite, but I will give you an analogy that will help you think about it. It's really, very bizarre. So here you want to somehow take a proof that may have a bug. You don't know how to find the bug, and translate it to another proof that, smears the bug everywhere. So it's easy to find by random sampling, right? But this process also has to, if it happens to take a correct proof, produce a correct proof. So it's not allowed to throw just bugs anywhere. So it's not clear how this would be done. But an analogy is error correcting codes. So in error correcting codes, I want to send you a message, and there's some noise, and we don't want to, my message, if I flip a bit, if I say I love you, a bit may flip it to I don't love you, and it will be a disaster. So so error correcting codes take messages like this and adds redundancy to them, so makes them longer. This is what happens in PCP also. In fact, PCPs use coding theory very heavily, very special codes, locally decodable codes. But anyway, it uses coding techniques to enlarge the message or enlarge the proof into one in which, right, in error correcting codes, the encoded message can be hit with noise in constant fraction of locations, and still you will be able to recover the correct one. So what happens in these PCP encodings of proofs is that if the proof was correct, then it will remain correct. If the proof was incorrect, well, I'm repeating what I said, an error will smear all over the place. So the recovery process, so in other words, let me say the contrapositive. If there were few errors, so few you could not catch them with a random sampling, then this corrupted proof can be converted to a real, honest-to-God proof. Right? That's a contrapositive. Shall I say it again?
It doesn't help.
It doesn't help. Okay.
You said that the proof relies on a very short message, and I don't.
No. The message can be long. No, not the message. No, in error correcting code, you are sending a zillion bits, but you want to distinguish between this sequence. Let's say you are sending 100 bits. You want to, or 1,000 bits. You want to distinguish between this message and a message in which one bit is flipped. All right? So the distance, between two legitimate messages is just one. Is the error or not? But after you error correct it, after you add the redundancy, then any two legitimate messages are encoded to sequences that are very different from each other. They differ in some constant fraction. This is the analog of the error being smeared. And it's not just an analogy, it's really heavily used in this field. Yeah.
Okay.
Yeah.
Yeah, one more question, Max.
Just make sure I understood. So zero knowledge proofs require the verifier to have access to randomness?
Yeah.
Okay, so there's no way to have zero knowledge with a determinism?
No, you can prove that, yeah.
Well, there's no more questions, so well, let's thank Adi again for doing that.